Good morning. We today start the second webinar of the CIRMET project. My name is Jakub Pluta. I represent ISNAP, the SME from Poland, and the dissemination partner of the CIRMET project. In the second part of our webinar series, we will focus on RECUWASTE technology proposed by CIRMET for the waste heat recovery systems for industrial applications. The presentations today, firstly, the presenter will be Mikkel Merchant from Technalia, which is the coordinating partner of the project. He will present shortly the overview of our project. And then the industrial partners will present firstly, there will be presentation from Davide Carando from Cemento Rossi regarding the heat recovery in cement industries, what challenges are still faced by these industries. Then Javier Calvino will present some insights in the RECUWASTE solution, and then it will be finished by Ibal Ulasia from Mondragon to present the flexible system for fluctuating energy demands. And after all the presentations, we will have the question-answer session. In your control panel, at the top of your screen, you have a question mark which you can use to ask the question to the audience during the presentations, and then at the end of the event, these questions will be answered. So thank you very much for attending this event today. And first, I would like to give the floor to Mikkel Merchant to present the project. So, Mikkel, the floor is yours.
Okay. Thank you very much, Jakub, for the introduction. And good morning, everyone. Thank you for attending this second session of this series webinars organized to present the technologies that are being developed within the European-funded CIRMET project. My name is Mikkel Merchant. I am a senior researcher at Technalia. I am also part of the team that, together with Maider García Cortázar and Guadalupe Lobo, are in charge of the coordination activities of the project. In this first presentation, I'm going to briefly show an overview of what the project consortium is developing. CIRMET is a project funded by the European Union Horizon 2020 Research and Innovation Program under this grant agreement. It has a duration of 4 years or 48 months, and the foreseen ending date is the 13th of September this year. The project has a budget to close to 10 million euros, and 15 partners from 6 different European countries with complementary profiles are part of the consortium. CIRMET project has the objective of designing, developing, and also validating at operational relevant environment a solution to provide energy and resource flexibility to energy-intensive industries. The project addresses some of the challenges on the industrial sectors which are considered as process industries. Some examples are cement plants, steel-making companies, and non-ferrous industries. These 3 sectors are represented by 3 different companies in the project consortium. Processing industries are characterized because they are huge consumer of raw materials, because they have to extract, transport, and process this raw material to manufacture semi-finished or high-quality end products. And they are also huge consumers of energy, because this manufacture is carried out by means of chemical, mechanical, or physical methods that, of course, needs energy and consume a lot of energy. Some of the challenges of the European process industries are facing more in particular are the following. The first one is the reduction of the dependency from third countries. In the case of raw materials, you probably know that some of these materials have been already catalogued as critical raw materials by the European Commission due to this dependency of third countries or because their availability is low. So we need to increase the recycling rate. And in the case of energy, I think we are all aware of the consequences of this dependency right now. The second one is the increase of the energy efficiency of the process unit operations. This way, we can reduce the overall energy consumption of the process, and this has an impact not only on the environment, but also, of course, in the competitiveness of the European markets. The third one is the adaptation of the production processes to the increasingly sustainable but highly fluctuating energy supply. This is related to the increasing share of renewable energies in the energy mix, which means that we can have a fluctuating availability of energy in the future, which means that we need to adapt the consumption of energy of the industrial processes to this new scenario. The next one is the reduction of fossil-based CO2 emissions, with the idea, of course, of fighting the climate change and try to reach the climate neutrality by 2015, which, as you know, is the main objective of the European Green Deal. And finally, and related to some of the previous challenges, we have the challenge of increasing the competitiveness of the European process industry so they can compete with the emerging countries. Most of these challenges have been considered in the design of what we call the CIRMET solution. Schematically shown, this solution can be considered as a process unit that can be integrated in an already existing process unit. The current process unit uses some raw material to obtain, using energy, of course, the main product, but also some byproducts and wastes that have to be managed somehow. So the idea is to take these byproducts and wastes, introduce them in the CIRMET solution, and through a valorization process, obtain a revalorized byproduct that can have a higher value in the market, and also some inner waste or inner slag that can also find a place in the market, and instead of finished being landfill, we can maybe use for other applications, such as in the construction sector, for example. Moreover, some materials can also be recovered from the process and eventually be introduced again in the process units, thus reducing the overall consumption of primary raw material. At the same time, some waste heat can be recovered in the process, and this way we can also reduce the overall energy consumption of the production process. And as a consequence, we can also reduce the CO2 emissions. So we can say that this solution has an impact, as explained, in the reduction of the primary raw material consumption, also in the increase of the energy efficiency, in the reduction of the fossil-based CO2 emissions, and in the reduction of the production cost. This solution is a modular solution, and it is integrated by 3 modules: a metallurgical furnace, an energy recovery device, and a digital platform. The first of the modules, the one that was presented in the first webinar held last Tuesday, and which video is already available on the project website and also in the YouTube channel, is the ephemeral metallurgical furnace to valorize industrial metallic wastes. This is done using a highly efficient, high-power thermal plasma analysis system, and also biogenic carbon obtained from biomass that is used as reducing agent. The second of the modules, the RECUWASTE, that is going to be presented today, is a waste heat recovery and storage system that takes waste heat from flue gases and transforms it into compressed air, with the possibility of adapting the energy generated to the compressed air demand through a continuous variable transmission system and an energy storage system. Finally, the third of the modules, the AFF 4.0 digital platform that will be presented in the last session of the series of webinars to be held next Friday, 3rd of June, is a platform that is composed by different physical and digital tools that are able to acquire and monitor the process parameters and also to predict and optimize these parameters, the parameters of the industrial processes to increase the quality of the products and increase also the efficiency of the process. Okay, now I would like to take advantage of this slide to thank all of you for attention, of course, but thank also the 15 partners that compose the project consortium for their good work and commitment. And of course, I will be ready to answer all your questions at the end of the webinar. And you have here my contact details in case you want to contact me anytime in order to have more information about it. Thank you.
Thank you, Mikel. So now I would like to ask Davide Carando from Cementi Rossi to present the challenges that the cement industry needs still to facing in case of heat recovery in this industry. So Davide, the floor is yours.
Thank you, Jakub. Good morning, everybody. My name is Davide Carando. I am the energy manager of the Cementi Rossi Group. The title of my presentation is Heat Recovery in Cement Industry, Challenges and Barriers. Okay. Cementi Rossi, let me say, it's an Italian cement producer whose market area is located in the north of Italy. Cementi Rossi has two cement plants located in the north of Italy. The first in Piacenza, 60 kilometers south of Milan, and the other one in Pederobba, 70 kilometers north of Venice. I have to start by giving showing you the cement process technology. We take stones and crush them, stones of limestone and marl, and then we grind them in the road mills, and we obtain a powder. This powder is cooked in a rotary kiln and quickly cooled in order to obtain a semi-product called clinker. The clinker is grinded in cement mills with other components, and we obtain all sorts of cement that we sell in bags or in bulk. The heart of the system is the burning system, composed by preheater, kiln, and cooler. In this burning system, we insert a mill at the top of the preheater. The mill passes through the kiln, is cooked up to 1400 degrees, and then quickly cooled down in the cooler, in the great cooler. In this way, we obtain clinker. We cool the clinker by blowing fresh air into the cooler. The stream of the air is diverted in two branches. The first one passes through the kiln, the preheater, and gets to the node. The other one passes through cyclones and then reaches the node. In this node, we have gases at the temperature between 300 and 400 degrees, depending on the number of the cyclones in the preheater. Part of these heat gases are used to dry raw material in the raw mills, about 20% of these gases. But the remaining part are waste gases that we cannot send directly in the atmosphere because they are full of dust, and we have to clean them in the bag filter. But we cannot send the gas at 300 degrees in the bag filter. So we are compelled to cool down them in a conditioning tower by spraying water. So the temperature of the gases are decreases from 300 degrees to about 150. There's a thermal loss, of course, in the conditioning tower. So we decided to install a heat exchanger to transfer the heat from the waste gases to an ORC system. So the gases, instead of passing through the conditioning tower, pass through the heat exchanger. But how we get electricity from the heat exchanger? Using an RC cycle, Organic Rankine Cycle. From the heat exchanger, the gases heat a carrier fluid. This fluid transfers the heat to a working fluid that expands in a turbine, and then is cooled and condensed in a condenser, and with the pump, the working fluid circulates. At the same shaft of the turbine, we connect a generator, so we get electricity. That's a conventional cycle. In the direct cycle, we erase one of the exchangers, so we increase the efficiency of the system. In a burning system, we obtain more or less 210 kilowatt-hour per ton of clinker from the preheater and 100 kilowatt-hour per ton of clinker from the cooler. In a medium cement factory with an output of clinker of 2,000 tons of clinker per day, we obtain 310 kilowatt-hour per ton of clinker. So it means a waste heat of about 25 megawatt thermal megawatt. 20% of them are used to dry raw material. We are remaining 20 megawatt. The heat useful for the RC is up to 150 degrees, so it remains about 10 megawatt. With an efficiency of 20%, we obtain 2 megawatt electrical megawatt. So with an RC, we save electricity from the grid, and then we avoid to emit CO2 in the atmosphere to make electricity. And then avoiding spraying water in the conditioning tower, we save water from wells and electricity for the pump to pump the water up to 30 meters. Time's rush. In Piacenza plant, our ORC is a direct cycle, so we have gases up to 350 degrees. We have installed a generator of 2,600 kilowatt. The electricity is totally auto-consumed at site, and the system is running from 2019. The average production is about 5,500 megawatt hour per year, and we avoid CO2 in the atmosphere of about 2,400 tons per year. And in the other cement plant in Pederoba, the gases are higher temperature, more than 400 degrees. So we could install a generator a bigger generator of about 4,000 kilowatt. Like in Piacenza, the energy is totally auto-consumed at site, and the system is running since last year. We estimate a production of about 8,000 megawatt hour per year. About the barriers, the main problem we are facing too is the high content of gases into the high content of dust into the gases. We're talking about 80-100 grams of dust per normal cubic meter. As the dew point of the gas is about more than 100 degrees, the inlet fluid of the working fluid is about 40 degrees. It happens that when the gases get in touch with the shell of the tubes, they condense and with the heat of the gas make a crust that decreases the thermal exchange. We try to solve this problem by making periodic cleaning of the heat exchanger, increasing the frequency of the cleaning system that in Piacenza is a hammering system, and preheating the direct heat exchanger in the starting phase before the gas inlet. There's not so great difference in the temperature between the gases and the shell of the tubes. Cool. Thank you for your attention. That's all for me, and that are my contact for any questions.
So thank you, Davide. And now I would like to ask Javier Calvino from Enerbasque to present us two presentations about firstly about RECUWASTE solution, and then more into the Organic Rankine Cycle units. Javier, you have the control now.
Okay. Thank you, Jakub, for the introduction. Good morning, everyone, and thank you for being in this webinar. My name is Javier Calvino, mechanical engineer and director at Enerbasque, and I'm going to introduce in these two webinars the RECUWASTE solution and sustainable and high-efficient overseas units developed in the CIRMET project. Sorry. Yes. In this first slide, I would like to focus the problem of the waste heat. According to the Lawrence Livermore National Laboratory, 58% of the total primary energy consumed in the planet is lost in different ways: cooling circuits, radiation, exhaust gases. With the CIRMET project, we want to provide a solution for a part of these energy losses, specifically the exhaust gases of the combustion processes. Okay. Currently, waste heat in industries is recovered or directly dissipated to the atmosphere. When it's recovered, it can be used in three different ways, and I say them from more efficient to less efficient way of use. First one, to preheat combustion air in gas burners. Second one, to transfer to other processes where it is needed. And the last one, transform it into electricity using an organic Rankine cycle. The solution developed in CIRMET project, the RECUWASTE, addresses the recovery of waste heat and transformation into compressor using an overseas unit. This RECUWASTE system has the following characteristics. The system is designed to recover heat from waste gases and transfer it directly into mechanical energy to feed an air compressor with possibility of storing. The system is designed to recover heat from waste gases and transfer it directly into mechanical energy to feed an air compressor with possibility of storing excess of energy. It is more efficient than the traditional overseas, as generator and motor are removed. Air compressor is directly generated with the shaft of the overseas expander, so the overseas doesn't need the generator and the compressor doesn't need the motor. And also includes some innovation that will be presented later along the webinar. The demonstrator is currently in testing phase, so results will be available in coming months. Okay. RECUWASTE is composed by a heat exchanger that recovers heat from the combustion processes such as gases, an overseas unit that transforms this heat into mechanical power, a continuous variable transmission CVT system, which adapts and transfers this mechanical power to the air compressor, and finally, both mechanical and electrical energy storage systems to store the surplus energy. This storage system can be used in alternate mode. This is when one is working, the other one is in standby. Okay, when the air compressed tank is full, here, and there is an exceed of waste heat available, we use the storage system to save energy. And when the air compressed is required and we have a lack of waste heat, we can use the energy of a storage system to return power to the system and generate more compressed air. Okay. Now I'm going to make a brief description of the components of the system. The heat exchanger is the first component of the RECUWASTE demonstrator, the one that captures the heat from the flue gases to transfer it to a working fluid. In our case, pressurized water loop. This fluid enters into the evaporator of the ORC unit to transfer the heat to the organic fluid. Sorry. A cell and tube heat exchanger has been the choice for RECUWASTE due to a combination of factors such as the large specific heat transfer surface or easy cleaning, among others. When recovering heat from dirty gases, problems such as the position of particles on the pipe surface, phenomenon known as fouling, wear or corrosion can be found depending on the specific composition of the gases and the amount and composition of the dust particles carried by these gases. This can be a limitation for the durability of the equipment, and it can reduce its efficiency, thus reducing the overall efficiency of the heat recovery unit. Sorry. In this project, some experiments have been performed. Different combinations of substrates and coatings have been prepared and tested in contact with the exhaust gases at Cementi Rossi's facilities for 5 months. The characterization performed after the trials has determined that some of the tested coatings can have a positive effect in reducing fouling, wear, and corrosion. Okay. Sorry. The organic Rankine cycle is placed between the heat exchanger and the transmission system. Heat is transmitted through the evaporator to the refrigerant loop of the ORC system, and afterwards, the thermal energy is transferred to mechanical energy by means of a twin screw expander. The ORC unit will be explained with more precision in the next section, so I will not enter in more details now. In the traditional ORC unit, the shaft of the expander will be connected to a generator to obtain electrical energy. However, in this project, the generator will be substituted by an air compressor, and between the expander and the compressor, a continuous variable transmission, CVT, will be installed to transfer the mechanical energy generated in the expander into compressed air at the end of the process. A transmission mechanism is placed between the ORC and the air compressor. You can see here in this slide. The objective of the transmission system is to take the mechanical power of the expander and transfer it to the shaft of the air compressor. By means of a clutch and CVT, the torque and power can be modified and adapted depending on the needs of the RECUWASTE system. And more details of this device will be presented by Ibai Eulacia from Mondragon University in the 3rd webinar of this blog. Finally, the energy recovered from the waste heat is converted into air compressed with a serial compressor directly coupled to the transmission mechanism with the electrical motor removed. And as we explained before, the system has the capacity to accumulate the exceed of waste heat when it is not needed. For that, we use a generator coupled to a battery rack that is here, or a flywheel that is here. And finally, a control system manages all the elements of the plant and makes the monitorization of all the variables defined with the capacity of saving data and communicate in real time with the other systems of the plant. Also, some wireless sensors have been developed in this project. And in this slide, is shown the final system overview and the main components, the control cabinet, the OSC, batteries, resistor, air tank, CVT, regenerative brake, and here in blue, the compressor. Okay. And the main innovation implemented in this heat recovery technology to transform heat into compressed air consists in the design and development of a mechanical continuous variable transmission (CVT) system that will permit to match the power supply with the compressor demand, with the possibility of storing the energy in a mechanical device such as a flywheel or in a battery pack through a brake or generator. This solution will avoid the loss of energy, and moreover, the possibility of storing the excess energy will permit to supply more energy than the generated by the recovery system in the moment when the compressed air consumption is high. Other innovations implemented are the substitution of current heat exchangers in the OSC unit by more efficient plate heat exchangers, the implementation of a magnetic sealing in the expander to avoid refrigerant losses, and the substitution of the currently used refrigerant by a less pollutant refrigerant. Validation tests are being carried out these days, and results will be available in some weeks. These pictures you can see here were taken a week ago in our test facility in Irún. And I would like to finish with a mention to a potential users of this technology: cement industry, glass industry, steel making industry, foundries, forging industries. All of them has a lot of waste heat, and this solution can increase global efficiency of the process and reduce the CO2 emissions. And that's all in this part. I will continue with the next one, with the ORC system. Okay, let's continue with the second part of my presentation. In the following slides, I'm going to introduce the Airbus ORC technology and main innovation introduced in the unit thanks to the CIRMET project. Okay. First of all, a short overview of Airbus. Airbus is an innovative company that designs and manufactures a small and medium ORC system dedicated to convert waste heat into power. We call them HRU, that means heat recovery units. We can recover heat from low temperature, 85 Celsius degrees, and get powers from few kilowatts up to 200 electric kilowatts. Main applications you can see here for our technology where waste heat can be recovered are gensets for electric power generation, engines for propulsion and power generation inside vessels, industrial waste heat for exhaust gases thermal heat recovery, waste valorization, and solar, thermal, and geothermal systems. Okay. Organic Rankine cycle is similar to a classical steam cycle, but the working medium is an organic refrigerant, which enables to use low temperature thermal sources, in this case, hot pressurized water coming from the heat exchanger that captures waste heat from flue gases. This water enters into the ORC at 115 Celsius degrees. Here is shown a scheme of our ORC system. Hot water, here in red, and heats the refrigerant in the evaporator up to the boiling point, and refrigerant turns into steam. Refrigerant steam enters in the Twain-Ski expander that transfers the energy of steam into mechanical energy. Expanded refrigerant steam goes through the condenser and is transferred back into liquid. The condenser needs cooling water coming from an aerorefrigerator, cooling tower, sea, or a lake. Refrigerant pump increases the pressure of the working liquid, and the cycle is repeated again. And why I try and study as expander technology? It is a robust and reliable. The expander is a reliable and simple machine which can expand, offering total warranties even in the liquid phase. That makes it possible to design simpler control algorithms with less protection than machines that use another type of expansion technology. The operation is simple. Airbus machines have been designed under plug-and-play principle with minimum intervention in their operation. They adapt perfectly to a wide range of working conditions, both for a cold and hot sources, with an automatic control system that seeks maximum efficiency of power production. Investment and maintenance cost is low. Expansion technology makes the cost of overseas machine CAPEX and OPEX very low. Avoiding complex lubrication system and the use of well-known technology mean that the ratio euro per kilowatt hour generated is the lowest possible. And finally, flexibility. Airbus machines might be adapted to a multitude of boundary conditions imposed by the installation. It is possible to design the machine for reduced space. Cooling can be made using the already existing installation, cooling tower, aerorefrigerator, or through a built-in condenser. The energy recovered may come from both gaseous and liquid hot sources. Okay, main innovations introduced in the ORC units are the substitution of the current heat exchanger by more efficient plate heat exchangers, magnetic sealing in the expander to avoid refrigerant losses, and substitution of the currently used refrigerant by a less pollutant refrigerant. Tubular heat exchangers are competitive and appropriate for fluids with high DIT content, as can be easily cleaned. But in the rest of applications, plate heat exchangers are simple, more efficient, and cheaper. The change of the heat exchanger reduces the CAPEX and footprint of an overseas machine. Indeed, welded plated heat exchanger of the unit avoid any loss of refrigerant. With the introduction of magnetic sealing system instead of the traditional ceramic seal, refrigerant leakage disappears and maintenance of the expander unit is reduced significantly, as the sealing system doesn't need any kind of intervention during its lifetime. Okay. Substitution of the current working fluid for a new with very low global warming potential is required by the EU regulations. Traditionally, ORC systems use R245FA as refrigerant inside the cycle. R1233ZD has a global warming potential of 1 instead of 1030 of the R245. This innovation makes the system more compact, safer, and environmentally friendly. Finally, the introduction of a regenerator in the system to preheat the refrigerant coming from the pump with the remaining heat released in the expander increases the global efficiency of the ORC unit. The regenerator is also a welded plate heat exchanger. And as I mentioned in the other session, validation tests are being carried out these days, and results will be available in some weeks. Here you can see in these pictures in the test facility. And this is all from my part. Thank you very much for your attention. I let you here in this slide my coordinates to contact me for further questions. Thank you.
Thank you, Javier. Now I would like to give the floor to Ibai Ulasia from Mondragon to present the flexible system for fluctuating energy demands. So Ibai, now the floor is yours.
Okay, thank you, Jakub, and thank you. Good morning, and thank you everyone for attending this last presentation. Yes, my name is Ibai Ulacia, and I'm from Mondragon Universitatea, yes, from the north of Spain in the Basque Country. I'm the head of the Structural Mechanics and Design Research Group, where we basically investigate the behavior of machine elements, such as gears, bearings, and so on. And we also develop different prototypes, test benches. Yeah. Okay, and in CIRMET project, we are leading work package 4. So this work package is the one where the RECUWASTE system and the concept has been developed, and now it is being validated, as previously said by Javier. Okay, my presentation today will be focused on the flexible system for fluctuating energy demands. And so I will try to, okay, doesn't work. Yes. Okay, so basically the idea is that to produce a waste heat recovery system, but flexible to adapt to different fluctuating energies, both in the demand and in the generator. So we can have more energy production than the demand, or in the other way around. So so for that, in order to absorb these fluctuations, we have developed a continuously variable transmission, and also some energy storage systems, like both mechanical and electrical ones. I will show you that in my presentation. So, okay. As it was already shown by Javier, this is how it looked like, the RECUWASTE system, but I will focus in my presentation with the CVT, or the transmission system here, and the energy storage system. And for that, I will use cycling for all of you to see these differences between the demand and the energy production. So if we have something like this here, so this is a stage, a very fluctuating state, let's say. So it is clear that we need different transmission ratios in order to get that. So if we will see here different scenarios, if we see, first of all, if the input torque is similar to the required torque, so then 1-to-1 ratio is needed. So the input velocity is similar to the output velocity, and the input torque similar to the output torque. If we move into the scenario where the input torque is higher than the needed or the required torque, then multiplier mode will be needed. In our case, that means that the tank is almost empty, the air tank is almost empty, so it is not opposing any torque to our system. So therefore, this multiplier mode is required. And in the other way, when we have when the required torque is higher than the input torque, then we have to put into reducer mode. It means that the velocity is reduced, but the torque is amplified. So that's how we can manage these different scenarios. So I think now it's more or less clear the need of this changing, and also if we have the possibility of storing if we have more energy than the required one, we can store it. So even the batteries or the flywheel, both we can have the energy there, and then we can use that energy when when needed, when the production is less or when the demand is higher than the produced one. So basically, that's the whole idea. I hope it's clear with this everyday situation for all of you. So now we can move on and see again the whole RECUWASTE solution. And here we focus in the central part. So we develop all this central part. We see the CVT and the regenerative brake with the batteries and the control and so let's move on and explain the specific innovations performed. So first, I will focus on the CVT transmission. So yes, the CVT, or first of all, I will have to say that this is a toroidal type continuously variable transmission. So it means that we have, and it's composed by the input and output disc, and we have some rollers in between. And depending on the position of these rollers, we can have different ratios. We see here in the right side if the if the rollers or the rollers are in this position and both radius are the same, so the input and output velocities are the same. If we move to this, if we tilt the roller, we could have other ratios. We can have in multiplier mode, or we can even have in reducer mode. So basically, that's the idea. We can move all. Okay, no, wait, the videos are not working today, but okay. Changing the tilting part of this roller, yes, we can have different ratios, and it is continuous because differently to other gearboxes or belt and pulley systems, we can change continuously from this mode to this reducer mode to the multiplier mode in all the toroidal cavity of the design part. So that's the main difference, that we can change continuously the rating. So that's why it is interesting in these fluctuating scenarios. So that's the idea. Okay. Here, okay, just the videos are not working, but here okay. In order to transmit all these loads, yes, this has to be preloaded. These rollers has to be preloaded, and because this force, this preload force, it goes to the traction force into the lubricant in contact, and this lubricant transfers this traction, transfers the torque from one disc to the other. So the idea here is to, okay, we need some sliding in order to transfer torque, but excessive sliding will just slide, and we won't transfer any torque. So we have here the play, or we have to play here with the preload, or the load we put into the system. If we put too much load, the life of these components will be low, and if we put very low load, it will slide, and we couldn't transfer any torque. So that's the idea. There is an optimum preload where the efficiency will be maximum and the life of the components will be safe. Okay, this is how it looks like, but I cannot show all the things in here because a patent application is in progress. I hope in the next, when it is applied, we will show. but it has been already done, and it is here. You can see here all the rollers, yes, all the rollers and how it looks like from the inside. So it has been manufactured and assembled, and we tested in our facilities first. So all this has been modeled in Simulink in order to predict the different scenarios. So we have all the ratios here, how to change the ratios, how the pressure will evolve in the tanks, and so on. So, and then we just went and test them in our test rig. So the test rig is basically 2 motors, as you can see here, and the CVT in the middle. Okay, so yes, basically we control the torque and velocities, and we change the ratios in between. Okay, and then we can see how with different torques, different sliding we get, and the same with different clamping forces, we get different sliding, and we see how the efficiency of the system changes relating to the sliding. Someone could think that low sliding is more efficiency, but that's not the case, because we need some sliding in order to transfer the torque, and so there are some optimum points, and there is some optimum points, and then regarding the efficiency, so we have to play with the sliding and the clamping force in order to get that optimum efficiency. Okay, I hope you understand it. Okay, and okay, there are other applications, so we just put the CVT in this RECUWASTE application, but it can be used for sure in many applications, from any vehicle gearboxes, in industry machinery, and even in energy generator, like wind turbines and so on. Okay, now I will move on into the energy recovery systems, and here we have 2 ways. One is the mechanical way, so with a flywheel, a kinetical energy storage system, and the electrical one. I will start with the flywheel development. Okay, and here, okay, the flywheel development, or the flywheels, are used in many different applications. Yes, from industry to even F1 cars, they have these curves, that it means kinetic energy recovery systems. So basically, the idea is to have a mass, or just a disk, rotating at different velocities or at high velocities, and then we have that kinetic energy to use when needed. So in this work, we have developed, so the idea is here to play with the specific energy, yes, the specific energy storage capacity, this value here, and you can get that by either with the increasing this ratio here, we use for that composite materials, and even with playing with this geometrical factor here. For that, we use topology optimization and 3D printed flywheels. Okay, and basically that's the idea. We look at different options, and we get this optimization, yes, this topology here, and we basically construct it in a modular way so that we can put different flywheels together, and we test them at high velocities, and we get this energy increase, and with mass reduction with these values of specific energy here. Okay, and the other way of yes, storing the energy is the regenerative brake, and in this work, the idea is that this regenerative brake has has a synchronous motor. In this way we can put a different speeds. So that's the main idea. So we can it is not a fixed velocity, and that's why we use a synchronous motor, an inverter, and then we put all this energy into this battery pack here. So if we look at the constructed system here, we have the reactive brake, pulley transmission. So the energy is coming from here, from the ORC. Yes, this is the ORC shaft is down here. So we connect it to the CVT here, and the connection to the reactive brake is done through this pulley here. And this way we can break it when the air tank is empty. We can break everything, and then we can play with this energy here, the ratio of the CVT here, and fill up the air tank. So that's the idea here. Okay, and I think that was all from my side. I will be, for sure, I'm open for all. I was a bit quick in the presentation, but I hope it was clear. And if you have any question, for sure, you can ask here now. You have my contact here, and you could also contact me at any time. I will be happy to answer to all of your questions. So that was all for my part.
So thank you, Ibai. So now we start with the questions and answers. We have some questions already. The first one is to Davide Carando. How much of the total energy consumption is covered by the ORC, and what is the gas composition?
Okay, let us say last year we got from the ORC about 5,500 megawatt hour against a total use of the electricity of 75,000 megawatt hour. So the ratio is about 7%. We expect to increase this value up to 10% in the next years. Very interesting the second question, because of course changing the composition of the gases, we change the specific heat capacity of the gases. The average composition is about 15% of CO2, 10% of oxygen, 69% of nitrogen, and 6% of water. And this gas, have we said before, has a high content of dust of about 80 grams for normal cubic meter. And that's all.
Okay, thank you. And now we have two questions to Javier. So the first one is it possible to use the RECUWASTE solution to recover heat from, for example, cooling circuits?
Yes, of course. It is easy to replace the flue gases heat exchanger and directly connect to the cooling circuit of any process. We just need a minimum temperature of 85 degrees Celsius to activate the ORC unit, and the cooling circuit can use water, thermal oil, or any other fluid.
Okay. And the next question, also to you, Javier, is as an ORC manufacturer, which do you think is the main barrier for the implementation of this kind of ORC-based heat recovery units in energy-intensive industries?
Good question. Well, for me, there are three questions. Mainly, the price of the electricity of that industry that normally is very low, and that makes the return of investment high. Also, the intervention and civil works to install the system, that is important. And the processes that normally are in batch. So it is necessary to install a big system only for a few hours a day, or the other alternative is to install a heat storage system to make the ORC process continuous. That is, it must be developed and it's not so cheap. So for me, that's the three questions are the main problems to install the systems.
Okay, thank you. And now I see there is one more question. So I think you, Javier, or Ibai could answer this. When do you expect that the RECUWASTE solution could be ready to be commercialized?
I can tell. We are doing tests these days in Tecnalia in Irún, and results are really promising, and we expect to finish them in the third quarter of this year. So we hope to commercialize the system at the beginning of 2023, more or less. I don't know if Ibai wants to correct me or.
No, I think you are right, Javier. We are finishing, so the system is already in the pilot plant in Tecnalia, so we are testing it now. As Javier said, the results are promising. So everything is done. Okay, everything could be improved, but all systems are working. It's, let's say, it is done, so it could be commercialized.
Okay, thank you very much. So this was the last question. So I would like to thank you to all the panelists and for their presentations, and also to all the audience who would like to register and take part in this event. You can follow the CIRMET project in the website and in social media. And soon after this webinar, we will publish the recording in YouTube and our website. So thank you very much, and hope to be with you in our next webinar on next Friday. Have a nice day. Goodbye.